Either physical and virtual buttons are a vital component in most input interfaces. However, button interfaces have some limitations. To this end, vibration-augmented physical buttons have emerged as a new alternative, offering advantages of both physical and virtual buttons. This simple technology affords programmable feels, using a single physical button. In this paper, we propose effective design methods for vibration-augmented buttons, and applying the methods to a real-world problem. We investigate the information transmission capacity of the vibration-augmented buttons, by adopting the information theoretic framework. In addition, we apply the findings to designing an effective text entry method for virtual reality. We implemented the hardware used in the previous research. We used 20 augmented buttons, by varying vibration frequency and energy, and the tactile sensations of buttons were distributed in a 2D effective space. To improve the information transmission capacity of the augmented buttons, we selected the buttons far from each other in the effective space, where the distance between 2 points means the perceptual dissimilarity between the two corresponding buttons. In addition, we used abstract meanings of button feels in the space to facilitate the user's recall. The information transmission capacity determines the recognition ability of the human tactile system regarding augmented buttons. In other words, it means how many augmented buttons can be perfectly identified from users. To estimate the information transmission capacity of vibration-augmented buttons, we measured the information transfer of augmented buttons, while increasing the number n of augmented buttons from 4 to 10. We selected the augmented button sets from the 4 quadrants in the effective space, while balancing both their perceptual qualities and physical properties. Participants were asked to choose the correct button among the n augmented buttons. The confusion matrices for the 4 sets are shown in this figure. The IT score was maximized to 2.6 bits, or equivalently, the participants near perfectly recognized 5 to 6 buttons, when more than 8 augmented buttons were presented. These distinctive perceptual and physical features with the effective space contributed to the identification of the vibration-augmented buttons. In the following experiment, we conducted another experiment to measure the information transfer of physical buttons. We selected 8 physical buttons, which had different operating structures and feels. Our experimental results showed that the IT score was 2.32 bits, approximately 5 buttons. The results suggest that physical and augmented buttons have similar information transmission capacities. Thus, this comparison advocates that augmented buttons provide distinctive perceptual and effective experiences to users. We implemented a VR application for typing text using a controller to test the expected benefits of augmented buttons. We made a mock-up VR controller containing an augmented button. Normally, the VR controller's physical buttons provide the same haptic feedback regardless of the system state. However, our augmented button enables event-driven variable haptic feedback. In this application, we designed 6 sensations for the augmented button to provide different confirmation feedbacks for different types of input errors. Users perceived a soft and blunt button feel when typing the correct character, and they attain different button feels when they make input errors, such as spelling error, capital letter error, spacing error, successive errors, and correction completion. Then, we conducted a user study that evaluated the benefits of our VR text entry application. Participants' task was to type the phrases with a virtual keyboard as fast and accurately as possible. They were presented with 2 different conditions during the text entry: single pattern, which always presents the same button feel regardless of their state, and multiple patterns with the selected 6 augmented buttons. The figure shows the results of task performance, such as word per minute, and error rate. The event-driven haptic feedback improved the task performance of text entry in VR. Furthermore, for all workload metrics and haptic experience questions, the mean scores of multiple patterns were higher than those of single pattern. The contributions of this work are a detailed analysis of the information transmission capacity of vibration-augmented buttons, and a successful demonstration of an interactive application using augmented buttons.